In this section, we're going to spend some time looking at polyprotic acid calculations. Now, I'm not going to spend too much time on this, and this will become obvious why as we move through these problems. But on the test, I may ask you some questions about, which acid is stronger in this polyprotic acid system, or is this chemical more likely to act as an acid or base, or something along those lines. And if you understand the concept of what I'm showing you, you should be able to solve these problems relatively easily. But I'm not going to give you a polyprotic acid Ka problem on the exam. So, I don't want to do any polyprotic acid problems, but I do want to talk about them. The problem with polyprotic acids is that because there's more than one acidic hydrogen, there's in fact more than one equilibrium. And what we tend to see is that these reactions are basically just the same. Ka1, the first hydrogen reacts, we get the conjugate base, NH0+. But this conjugate base still has some acidic properties. So in fact, you can take that HCO3- because it still has an acidic hydrogen. We can lose the second hydrogen as well to form CO3-2-. Now, this is going to be a much less favorable reaction than the first one. And part of the reason is that it's already given up a positive hydrogen. So now we have a negative charge. So things that are already negative charged generally do not like to give out positive charges except a very, very limited number of times. So what we tend to see is the more hydrogens you lose, the less likely you are to lose another hydrogen. So these acids get weaker and weaker and weaker. And we can see that here. There's ascorbic, we start out 8 times 10 to the -5th. The second one is way out at 10 to the -12th. Citric starts at 10 to the -4th, then 10 to the -5th, and then 10 to the -7th. Those are all pretty close together, actually. But you can look at phosphoric, starts out at 7.5 times 10 to the -3rd, and then 10 to the -8th, and then 10 to the -13th. It just gets weaker and weaker and weaker every time you lose a hydrogen. So let's look at what happens mathematically here when you have these very, very different Ka values. Okay, so if we start with a 1 molar concentration of H2CO3, right, well, we just do these 1 Ka at a time. So if we start this with H2CO3, that's going to dissociate. Again, we can assume that it dissociates almost 0%. So 1 minus x is basically just 1. Cross multiply, solve, we get x equal to 6.55 times 10 to the 4th H0+. Okay, so the pH from the first dissociation alone, we just take the log of that H0+, and we get a pH of 3.18. Okay, which is actually, pretty acidic. Here's the problem, right? The second dissociation only has this much acid in it. And so it really doesn't have very much acid to start. So we get to the second dissociation, and we have a couple of problems. The first of all, we have a much weaker Ka value of 5.6 times 10 to the -11th. So that's problem 1. Problem 2 is that we don't have very many reactants. Any reactants we have to be created from step 1. So in step 1, we have 6.55 times 10 to the -4th HCO3- created. That's all we can start with. And the third problem is that we already have a really, really large concentration of H3O+ in this solution. In fact, we have the same concentration of H3O+ in the solution as we do for HCO3-. So since we already have some products in solution, this reaction is not going to go very far. So what we need to do here is plug in our Ka, set up our HCO3- concentrations and our H3O+ concentrations into our ice table. And then when we solve, we're basically going to make the assumption that x is really, really small. And that's a perfectly reasonable assumption to make. In fact, what we're going to find is that x is equal to 5.6 times 10 to the 11th. Now, once you realize that, right, and we have our H3O+ concentrations from our 2 steps, 6.55 times 10 to the 4th and 5.6 times 10 to the 11th. Well, that second dissociation has no impact on the pH at all. It's so much smaller than the initial concentration. It's, like a million times, maybe even 100 million times smaller than the H3O plus we got from the first step. And so the pH is going to stay completely unchanged for the second step of dissociation. For that reason, I don't like to do these problems very much. I think it really makes life a lot more complicated. If you were to see this somewhere, and I have seen professors give out this problem, I would generally find the pH for the first step and then just assume it's not changing from there. Usually, if they give this kind of problem, though, they do expect you to run through the process and demonstrate that the second step has very, very little change. What I do often ask for is to just kind of be aware of what Ka1, Ka2 means. So just take a second and write out the Ka1 and the Ka2 for the dissociation of sulfurous acid and for the dissociation of phosphoric acid. Okay, so again, these are not a big deal. We have sulfurous acid reacts with water. We get the bisulfite ion plus H3O plus. The Ka2 is just going to be the reaction of that bisulfite ion plus water to get the sulfite ion and H3O plus, right? So that's our Ka2. For phosphoric acid, we're going to start with phosphoric acid. Reacts with water, we get this hydrogen phosphate and H3O plus. That negatively charged ion then loses another hydrogen to form this monohydrogen phosphate. Again, even less acidic. Technically, you can still react this one more time to get rid of one more hydrogen to form the phosphate ion. As you can imagine, this last reaction is not very acidic at all. And as a result, we don't form very much phosphate ion.